Hi everyone, today we're going to talk about marginal analysis. In business and economics, marginal cost is the amount that cost changes based on making one additional item. So marginal cost is C of x plus 1 minus C of x. Marginal revenue is the amount the revenue changes based on selling one additional item. So marginal revenue is R of x plus 1 minus R of x. And finally, marginal profit is the amount the profit changes based on selling one additional item. Marginal profit is P of x plus 1 minus P of x. So in all of our cases, whether we were looking at revenue, profit, or cost, we were always looking at making one additional item. We can take this and kind of compare it to slope and see that that's what slope kind of tells us too. It says, how are we changing? So if we go from a point x to the next point x, how did our y change? Did it go up? Did it go down? In calculus, when we do that, how do we talk about slope? We use derivatives. So derivatives mean we want to look at the slope of the tangent line. The tangent line helps us out a lot because instead of looking at how is it going to change between two different places, we can look at the instantaneous rate of change at a value x. So let's put that all together and say the definition of marginal cost, revenue, and profit from a calculus standpoint is that the marginal cost is the derivative of the cost function. The marginal revenue is the derivative of the revenue function. And then the marginal profit will be the derivative of the profit function, but many times we'll end up getting there by taking the derivative of the revenue and subtracting the derivative of the cost. Important to note that the marginal functions are going to give us a good approximation of the actual change of the function as they increase in production. We won't get exact values all the time, but it'll be close enough that it won't make a big difference. So this tells us that the marginal cost, C prime of x, is approximately C of x plus 1 minus C of x. Marginal revenue, R prime of x, is approximately R of x plus 1 minus R of x. Then marginal profit, P prime of x, is approximately P of x plus 1 minus P of x. We need to do a bunch of examples to really feel like what does that look like when we put in numbers. Number 1, the price for which x thousand headphones will sell is P equals 150 minus x over 3. Part A, we want to find the domain of the function. We know a couple things. We can't sell negative headphones. The smallest number of headphones we could sell would be 0. We can see the number of headphones we sell will increase as the price decreases. So there is a point where as the price is decreasing, it's going to intersect the x-axis, and we want to find out when that occurs. That's where the revenue will be 0. We have a couple of ways to do it. One way would be algebraic. We can do 150 minus x over 3 equals 0. That says 150 equals x over 3. Or 450 is x. You could also choose to go to Desmos and graph it. So I'm writing P equals 150 minus x over 3. And you don't see anything over here, but if I were to zoom out, you can pick up the line. We can put over here that we know x had to be greater than or equal to 0, so I'm going to say 0 is less than or equal to x, and now it starts at 0, and you can see they intersect at 150. But you could also go over, so let's pull our graph over, and when I click on the line, it tells me the intercept is at 450. So let's add that on our other side, less than or equal to 450. And now we have this nice line with a beginning and ending place to represent our function. B says find the revenue function. Revenue is price times quantity. So we're going to take our price, which was 150 minus x over 3, and multiply that by x. Because we're going to use this a bunch of times, it's going to help if we multiply that out. So I'm going to distribute the x. I have 150x minus x squared over 3. Part C says find the revenue for selling 5,000 headphones. Part D says find the revenue for selling 6,000, and then E we're going to find the difference. So we're going to find that marginal revenue of how did the revenue increase when we went from 5,000 to 6,000 headphones. Again, let's make this simple. Let's bring in Desmos and let it do the heavy work. So I'm going to write R of x is equal to 150x minus x squared divided by 3. Because we want to see the individual values, I'm going to type in R of 6, R of 5, and then R of 6 minus R of 5. Okay. So R of 6 says it was 888, R of 5 was 741.67, and the difference between those two was 146.33. This says when the number of headphones sold increases from 5,000 to 6,000, then the revenue will increase by 146.33 thousand. In comparison, let's find the derivative. We had that R of x was equal to 150x minus x squared over 3. And remember, we can express that as 150x minus 1/3 of x squared. The derivative, 150x, just becomes 150. The 2 comes down with the negative 1/3, so I have negative 2/3 of x. Now I can find the derivative of r when x is equal to 5. I have 150 minus 2/3 of 5. I'm going to do 150 minus 2/3 of 5, and I get 146.67. We can still see the 146.33 we got from doing R of 6 minus R of 5, and now we have R prime of 5 is 146.67, so a very close approximation by doing the derivative. Let's try a few more numbers. Let's look at selling 25,000 versus 26,000, and then let's do the difference of those two. So I'm just going to go back and type where we had before. So the 6 I'm going to make 26, the 5 I'm going to make 25, and I'll do that same thing with the subtraction, so I can just type right into it. So here's what we have. At 25, it was 3,541.67. At 26, it was 3,674.67. And the difference between those two was 133. So when we increase the number of sales from 25,000 to 26,000, then that increases our revenue by 133,000. We want to, one more time, use the derivative to figure out what happens at 25. So remember that was 150 minus 2/3 of our x value, which was 25. So I'm just going to go back to what I had earlier, change that 5 to a 25, and it says the expectation from our derivative is that it would be 133.33. Again, a very close approximation between subtracting the values and finding the derivative. Let's do it one more time. Let me just make sure we really know what's going on. So let's try 225 and 226. You know what I'm going to do? I'm going to change this to 226 in Desmos. I'm going to change it to 225. Same thing for the subtraction. And then same thing in my derivative. So 226 says 16,874.67. 225 said 16,875, which gave us a difference of negative 0.33. The derivative shows that R prime of 225 was 0. Again, different as it has been every time, but again, very small values, very close to each other. So we're not seeing a big difference in revenue if we increase production from 225 up to 226. Let's look at one more just to see other things that can happen. So this is going to be 250 and 251. So let me write 250. There's our revenue. Let's do 251. And then I want to subtract 251. Put the big one first, put the smaller one second, 250. So the revenue for 250 was 16,666.67. For 251 was 16,649.67, which gave a difference of negative 17. So we can see the revenue is going down even though the number that we're selling is going up. Then if we put 250 into the derivative, so let's go back to our derivative and put the right number, it also shows a negative. We have negative 16.67. So this close approximation from doing the marginal revenue with a derivative. Let's try a different marginal function. Let's look at cost. So this time I have C of x is 48x plus 1,250. We're going to do similar numbers. I have the cost at 6 minus cost at 5, cost at 26 minus cost at 25. Okay. let's type in C of x was equal to 48x plus 1,250. And we want to do C of 6 minus C of 5. Then we're also going to do C of 26 minus C of 25. Now notice both times we got the same value of 48. So we got 48 for C of 6 minus C of 5. We also got 48 when we did C of 26 minus C of 25. Now why did that happen? Well, go back to our original function. C of x is 48x plus 1,250, and let's find the derivative. Well, the derivative of 48x is 48, and the 1,250 goes away as a constant. So if I find the derivative at 5, I get 48. Also, derivative at 25 would be 48. So this time, complete agreement between all of our values. We're going to use that same function again, and we're going to find the average cost. So the average cost would be take the 48x plus 1,250 and divide it by x. You could, if you wanted to, go ahead and separate that. 48x over x would be 48. And then the 1,250 would be x to the negative 1. But totally up to you how you want to use it. If you decide to use it this first way, I'm going to put parentheses around the numerator just to help put in that order of operations for me. Now we're going to go back to those same values, 6, 5, 26, and 25, and see what's happening to the average cost as we change the level of production. I can be a little lazy here and just throw parentheses around the numerator, and then hit divide by x, and it'll go ahead and give me the values. So the average at 6 minus the average cost at 5 decreased by negative 41.67. And the average cost from 26 compared to 25, it shows a decrease by negative 1.92. Cost going down is great because when cost goes down, profit can go up. Let's compare this to the marginals using the derivatives. So what do we have? We have that the average cost is 48 plus 1,250 x to the negative 1. So our average cost, 48 plus 1,250 x to the negative 1. We take the derivative. The 48 is a constant. We don't have it anymore. The negative 1 comes down, so I have negative 1,250 x to the negative 2. Now we're going to plug in 5. So I have negative 1,250. 5 to the negative 2, which is the same thing as negative 1,250 over 5 squared. This is negative 50. And then if we do the same thing with 25, we have negative 1,250, and I'm just going to put it as 25 squared. I get negative 2. For number 3, we're going to graph both the revenue and profit function using Desmos, and then look at the break-even point. We want to look when is the profit positive, and over what price is the profit positive. So there's a lot to go on. The first thing we should probably do is remind ourselves what we had. So we had a revenue function that was equal to 150x minus x squared over 3. And we haven't done the profit function yet. We did the cost function. So to get profit, we need to do revenue minus cost. So we can do our profit as 150 x minus x squared over 3 minus our cost function, which was 48x plus 1,250. When you distribute the negative out, you end up with 150x minus x squared over 3 minus 48x minus 1,250. So I can put the 150 minus the 48, that becomes 102x minus x squared over 3 minus 1,250. So here's our profit function. When we start thinking about what domain we should use and what our viewing window should be, we should go back and remember that we had a closed domain of 0 to 450 when we talked about the price. So we want to use that same thing to talk about the revenue and the profit. So I'm going to start with my revenue. So R of x is equal to 150x minus x squared over 3. And I'm going to put 0 is less than or equal to x, which is less than or equal to 450. That way it doesn't go more than it needs to. And I'll do the same thing for the profit. So the profit was equal to 102x minus x squared over 3 minus 1,250. And let's put that same domain. We can still have negative values for the profit. We won't have negative values for the revenue. And then let's go over and change our settings. On the settings, let's start out 0 to 450 so we can see our domain. And then we are going to have both positive and negative on our y values. Why do I know it's going to be negative to start? I have this negative 1,250 I could look at, so I knew to make it negative. So I put some big values in, like negative 1,250, and then also capped it a little high, like 20,000. Then you can kind of zoom around and use your mouse, because I don't expect you to always know what the range should be, but once you have something in there, it's easy to manipulate. Let's look at what I asked for. I said, let's start with the break-even points. The break-even points is where the profit is 0, so I'm going to click on the profit, and I can see there's one at 293.21, and there's one at 12.789. So I have break-even points at x equals 12.789, and also at x equals 293.21. Then it says, for what intervals is the profit positive? So positive is from the 12.789 over to the 293.21. Open 12.789 to 293.21. The reason it's not closed is at these points it's equal to 0 and 0 is not positive. We also should look at where the revenue is positive. So the revenue is the red, and that goes from our beginning 0 over to our end 450. Again, I'm going to make it open to show not equal to 0, only positive values. Number 4 says the total profit in dollars from the sale of X boat trailers is P of X is 1,450X minus 0.35X squared minus 5,000, where X is greater than or equal to 0 and less than or equal to 4,000. This time the domain is given by definition, so we don't have to worry about why is it that, just know that that's what it is. Part A says find the derivative, so P prime of X is equal to 1,450X is 1,450. Using the power rule, negative 0.35x squared becomes negative 0.7x, and the 5,000 goes away. Now we're going to find P prime of 5 and interpret the number. P prime of 5 is equal to 1,450 minus 0.7 times 5. This is 1,446.5. This says when sales increase from 5 to 6, then the profit goes up by 1,446.5. So profit increases $1,446.5 when sales increase from 5 to 6. We're going to do the same thing now, but we're going to plug in 100. So P prime of 100 equals 1,450 minus 0.7 times 100. This gives us 1,380. So profit increases $1,380 when sales increase from 100 to 101. Then we're going to do it the old way, the long way, where we plug this into Desmos. So we're going to put in 1,450x minus 0.35x squared minus 5,000, and we're going to do P of 6 and P of 5. So I put that in and I got 1,446.15. So you notice it's only cents off. So we had 1,446 in both. One says 0.5, one says 0.15. Let's try again with 101 versus 100. And I got 1,379.65. Again, a really close approximation between the actual, putting in the two values, and using the derivative to approximate it. Our last example today. The total cost in dollars of making X coolers is C of X is 0.04 X squared plus 4.5 X plus 4,900. We're going to find the average cost per unit if 1,000 coolers are produced. Then we're going to find the marginal average cost per unit if 1,000 coolers are produced. So let's start by saying we need the average cost. We're going to take our cost 0.04 X squared plus 4.5 X plus 4,900. And we're going to divide it by X. If you want to, you could go ahead and divide by X. You would get 0.04X plus 4.5 plus 4,900 X to the negative 1. So I divided each of those three terms by X. Part 1 says plug in 1,000. So let's go back to Desmos and do it that way. So I have C of X equals, I'll do it as parentheses, 0.04 X squared plus 4.5X plus 4,900 divided by X. Now we can do C of 1,000. So it says the average price per cooler when we make 1,000 is $49.40. Now we're going to find the marginal average cost. So the marginal says we need to take the derivative of the average cost function. So using the 0.04x plus 4.5 plus 4,900x to the negative 1, I have 0.04x, which becomes 0.04. 4.5 is a constant, it goes away. Using the power rule, the negative comes down. I have negative 4,900x to the negative 2. We want to plug in 1,000. We get 0.04 minus 4,900. I'm going to put it over 1,000 squared, which is negative 0.0449, so I'm going to call it negative 0.04. So it says using the results from A and B, estimate the average cost per cooler if 1,001 coolers are produced. So before, we had that the average cost for 1,000 was $49.40, but we know that they're reducing by 0.04 cents, so minus 0.04 gives us an estimate of $49.36. Let's do one more. We have find the marginal average cost of 350 units. So we're taking the marginal average cost, which was 0.04 minus 4,900 over X squared, and we're going to plug in 350. So 0.04 minus 4,900 over 350 squared. I get negative 0.08. This says that the average cost per unit will decrease by 8 cents when we increase production from 350 to 351. Still, important to always look at, we're looking at the smaller amount, so this was 350, and looking how it provides change. So we'll say the average cost decreases by 8 cents when the 351st cooler is produced. So it went from 350 up to 351, and this is where we captured the saving, is on the next item.